Hello everyone, I am Sukumar from Civil Engineering Department of Northeastern Regional Institute of Science and Technology. So I would like to discuss an example problem involving nonlinear static analysis of a geotechnical structure using Salome-Meca 2017. I hope you are familiar with the software suite called Salome-Meca. It's a free open source software provided by EDF France, and I'm going to use the version 2017 in this tutorial because this is a revamped version having a new module called Code-Aster study. If you are not familiar with Salome-Meca in general or Salome-Meca 2017, you please consult relevant tutorials. There are many tutorials, good tutorials available in YouTube and other sites as well. So let us see what we are going to discuss here. First, I would like to give you some very basic introduction to nonlinear finite element analysis and why nonlinear finite element analysis, in short NFEA, are needed, and what are their differences with compared to linear finite element analysis. Then I'll discuss very briefly what are the sources of nonlinearity in an engineering problem and what are the solution strategy for a nonlinear problem, basically solution of nonlinear equation in the context of finite element analysis. And then I will take up the example of the slope structure, a slope structure made up of Moore-Coulomb soil, and we will analyze the stresses and strains for its self-loading. So this is my plan of presentation. So first, what is nonlinear analysis? When the equations, the basic equation, the both left hand and right hand side of the equations depend on the primary unknown quantity, then we can call it as a nonlinear equation. And in finite element method, you know that those are matrix equations, and if the both right hand side and left hand sides are dependent on the unknown, primary unknown, then we call it nonlinear equation. For example, in a static problem, the basic finite element equation is this: K matrix, the stiffness matrix, times the displacement vector U gives me the force vector F. So here in this case, this force vector and stiffness matrix is not dependent on the unknown U, and they can be solved relatively more easily, and that's why it is a linear problem. On the other hand, in a nonlinear problem, this stiffness matrix will be the function of the unknown displacement U, and similarly the force vector at a given stage of solution will be depending on the unknown displacement vector U, and that's why we need to apply the nonlinear equation fundamentals to solve this kind of an equation. So that is what is nonlinear finite element analysis. Now, before embarking on nonlinear finite element analysis, we must be clear about the physical problem at our hand we are going to solve. The basic physics of the problem must be very clear, and it also must be clear how that basic physics has been modeled in terms of the finite elements, in terms of the various material models available in a given finite element software or suite. So this physical insight and the corresponding mathematical formulation, understanding about these are very important. Otherwise, the use of the software will be done like a black box, and therefore if there is a famous saying in any computer analysis that garbage in is garbage out. So to avoid that black box syndrome, we must have understanding of the physics of the problem and also how it has been formulated mathematically in terms of the finite element equations. These are important. Now, where do we need nonlinear FEA analysis? These are some examples I have listed. Strength analysis of structure, how much the load the structure can carry before it fails. Then stability analysis, then reserve strength analysis, then progressive failure analysis, how the failure initiates in a given situation, in a given structure, and how it progresses till the collapse of the structure. So when we want to study those things, then we need nonlinear finite element analysis, because all these problems are basically nonlinear problems. Another example from mechanical field is simulation of metal forming or extrusion or casting processes, etc. Then also nonlinear finite element analysis is very much used in research. There are various research needs in an industry, like we need to establish simple code-based analysis and design methods. We need to verify their accuracy many times. Then we need to understand the behavior of a structure or any new product. In order to understand the behavior, we need to simulate it. And also many times we need to validate the proposed constitutive models, that is how the stress strain relationship is mathematically formulated in order to do the nonlinear analysis. In order to validate those material models or constitutive models, we need this NFEA. So these are some of the areas where NFEA is used. Then also there is another important region becoming more important these days. Since the computer power per unit cost is increasing day by day, we are having powerful hardware at decreasing cost, and also we have many viable, robust, very good quality open source FEA suites in addition to various commercial finite element softwares. I believe the engineers should take advantage of this increasing computer power, both in terms of hardware and software, and therefore now it is feasible to apply direct analysis rather than code-based design in a given engineering practice. So that is another reason why we should learn NFEA. Then let us see the key differences between linear and nonlinear FEA. They are quite different. I have listed some of the key differences, important differences. In case of linear analysis, since the system is linear, therefore we can apply superposition principle, and thus we can superpose the analysis results from different load cases in case of a linear analysis, whereas this thing cannot be done in nonlinear analysis because this superposition principle does not remain valid in a nonlinear case, and therefore only one load case can be handled at a time in a nonlinear analysis. And in most of the cases, almost all the cases, the loading history is quite important in a nonlinear analysis. The effect of loading history on the response of the structure becomes important, and also this effect of loading history is not there in linear case. That's why we can apply the superposition principle, whereas this is not possible in nonlinear case. And obviously, since the behavior of the structure is nonlinear, therefore the response, we should not expect that will be proportional, directly proportional to the loading. Now, while doing nonlinear analysis, we need to identify some key or appropriate measures in terms of which we will determine the structural behavior, and that needs careful thought of the given problem at hand. What is the appropriate measure? That depends on the problem at hand. For example, if I am analyzing a foundation for its ultimate bearing capacity, then the load deformation behavior of the footing will be important for me. That will give me a measure of failure. On the other hand, if I am doing a slope stability analysis, then might be the deformation at the slope surface or the strains developed within some particular region of the slope, the failure surface. Those might be a better indicator of failure. So what kind of appropriate measure we will take, that depends on the problem at hand. And also in nonlinear analysis, the initial state of stress before the analysis has been started, or the state of stress at the current state of analysis, will affect the future state of stress and strains during the analysis procedure, and that's why the initial state of stress is very, very important. Next, let us see what are the sources of nonlinearity. We have basically three types of nonlinearity. One is geometric, the other is material, and the third one is because of the boundary condition nonlinearity. So first one is geometric nonlinearity, when we need to take into account the change in geometry as the structure deforms in the formulation of the stress strain relationships and finally the equilibrium equations. Then we call that structure to be geometrically nonlinear. So it is a case of geometric nonlinearity. And the application areas of this geometric nonlinearity are analysis of slender structures, metal forming, stability of structures. In finite element terminology, we call them large deformation or large strain problems. So mathematically describing, the strain displacement operator, which relates the strain to the displacement, is a nonlinear operator which depends on the displacement itself, and that's why it is a nonlinear problem. Next is our material nonlinearity. In material nonlinearity, the material response is such that the stress strain curve is nonlinear, and therefore the current state of stress in the material depends on the current deformation, and also in most of the cases it depends on the past history of deformation. And when we need to deal with such materials like soil, our problem will be a materially nonlinear problem. And these are the application areas I have listed: nonlinear elasticity, plasticity, viscoplasticity, creep analysis. So these are the areas where material nonlinearity comes into picture. Mathematically, the stress strain law we normally define by generalized Hooke's law in a linear case, but here in this case this constitutive matrix is a nonlinear matrix, so the material behavior cannot be expressed in terms of generalized Hooke's law. So here the sigma is dependent on the nonlinear operator C and the change in strain, where this epsilon's naught is my initial strain. That's how it depends on the previous loading history. Then we have boundary condition nonlinearities, and since we have two types of boundary conditions, mainly force boundary condition and displacement boundary conditions, therefore this nonlinearity can be divided into two categories. The first one is forced boundary condition nonlinearity, and this arises when the applied force depends on the deformation. For example, if I am analyzing a structure under hydrostatic pressure, since hydrostatic pressure acts normal to the surface, therefore as the structure deforms, that normal direction will change and accordingly the load will keep on changing. So this is an example of force boundary condition nonlinearity. So in mathematically, the prescribed surface tractions and the body forces, those will be functions of displacement in this case. The other is the displacement boundary condition nonlinearity. When the displacement boundary condition depends on the deformation, then we call it displacement BC nonlinearity. And a famous application area is the problem of contact of two bodies, because there the prescribed displacement in the contact surface depends on the deformation of the two contacting bodies. So that's why it is a nonlinear problem. So these are the main sources of nonlinearities in an NFEA. Next, as you are familiar with solution of nonlinear equations needs to be solved in an iterative manner, and the same strategy is useful in case of finite element analysis also. And here of course I will not prepare any new presentation file. I will use very good presentation files already available in the EDF website, Code-Aster website. Another advantage of using those files will be that the terminologies related to Salome-Meca are used there, so we will also become familiar with some of the terms used in Salome-Meca for analyzing the nonlinear problem. We use iterative solution, incremental algorithm, so all those things I will discuss by using the Code-Aster presentation file from EDF. In a nonlinear problem, we cannot apply the load in a single go, because that will be too much nonlinear to solve practically, and therefore what we do to cut the nonlinearity, we apply the load in terms of various load steps. Okay, that will reduce the level of nonlinearity in the problem, and that will ease the process of solution. So those load stepping etc. I will discuss, and again I will use their file for that purpose. Then a famous method of solving nonlinear equation is Newton or Newton-Raphson method. There are also some variations of this original Newton-Raphson method, Those are called modified or quasi-Newton method. So some of those methods are implemented in Salome-Meca, including Newton's method and other modified Newton's methods. So those things also will have a discussion before we actually do the analysis in the Salome-Meca. This is the general workflow in Salome-Meca 2017. So all these steps will be discussed one by one and will be demonstrated how we can implement these steps by an actual solution in Salome-Meca. So this completes this tutorial. Hope all of you enjoyed it. So see you in the next tutorial. Thank you.